In this video, we're going to talk about what activation energy is. So activation energy is an energy barrier that has to be overcome to allow the reaction to occur. And it's the amount of kinetic energy that reactants have to allow for effective collisions and chemical reactions to occur. So if we take a look at the progress of a reaction, we have our reactants. There needs to be some sort of successful collision to occur, and then at that point where that collision is occurring, that's where we have the activated complex. So the bonds haven't quite broken and the new bonds haven't formed, so at that point the activated complex has more potential energy than the products or the reactants. In that transition state, those bonds break, new bonds are formed, and then we form our products. And this part here, the amount of energy that is from the reactants up to that transition state is known as the activation energy. And then the amount of energy from between the reactants and the products is known as the delta H. So in this example, this delta H is negative. It's a drop in energy from reactants to product. So this must be a release of energy, which is known as an exothermic reaction. So as I just mentioned, exothermic reactions involve a release of energy, and the products have less energy than the reactants, so the delta H is negative. So if we look here, from the reactants to the top where the transition is, that's the activation energy. And then from where the reactants are to where the products are is the delta H, or the enthalpy change. Now, endothermic reactions absorb energy, so the products actually have more energy than the reactants. So the delta H is positive. So if we take a look here, our reactants are way down here. There's a lot of activation energy required to get to our transition state. So this is our activation energy here, and then this is our enthalpy change, or delta H, from the reactants to the products. So in chemistry, we tend to use the Kelvin scale. And the reason why is when we double the Kelvin temperature, we're doubling the kinetic energy at the same time, because the average kinetic energy is proportional to the Kelvin temperature. So while we're more used to using the Celsius scale, it's much more important that we use the Kelvin scale, because then we can use these proportional relationships to determine the kinetic energy of the reactants or products. So we just need to remember that we need to add 273 onto our Celsius values to get our Kelvin temperature. So remember, it's an absolute scale. 0 Kelvin is equal to negative 273 degrees Celsius. Freezing for Celsius is 0, but that's 273 Kelvin. And then water boils at 100 degrees Celsius, which is 373 Kelvin. So catalysts, we sometimes say that catalysts lower the activation energy. That's not really true. What catalysts do is they provide an alternative pathway that has a lower activation energy, and they're chemicals that help a reaction along by providing an alternate pathway, but they're not a reactant in the equation. They're just there to help things along. So they speed up the reaction without getting used up themselves, and they do so by providing an alternate pathway. So we have a lower activation energy because there's an alternate pathway. Now, inhibitors are the opposite of catalysts. They slow down reactions, and the way they do that is they either bind to the reactant or to the catalyst themselves, preventing the reaction from occurring and slowing down the rate of reaction.